Welcome to the first open source office hours hosted by AccuKnox. We got on hand deck today, we have Rahul Jadhav, who is going to walk us through some of the early use cases for KubeArmor, the open source. We will be sharing this recording with all of our attendees, and feel free to ask questions. We'll get to those later. Anything is offline, we can get follow-up later. We invite everyone to join our Slack channel and go to GitHub and check us out. So we're starting with system policy enforcement using KubeArmor. We're going to go through a series of overviews before we get into a demo. We got what is KubeArmor, KubeArmor differentiation, installation and deploying sample policies, and getting alerts to telemetry information for the policies. With that, I'm going to send it over to our demo host today, who's going to walk us through some of these early items for us. So we'll take it away.
Thank you, Jeff. I should be able to share my screen, right?
Yeah, please. If you can't, let me know.
Here I go. So before we get into the demo and some of the differentiation point, let me quickly introduce what KubeArmor is. Most of the time, most of the people have heard, may not know about what system policy mean. So let me first clarify about that first before going into the details of what KubeArmor can do. So the system policies, when we say system policies, what I mean is how can we limit the access of pod as to what it can do from the system's perspective. So the system's perspective could be what all different processes can be spawned within that pod or within a container, what kind of file system path accesses could be made within the container or a pod, what kind of capabilities can be made use of with by a given container or a pod. And so all these are the questions that any systems policy enforcement engine should be able to handle, and KubeArmor is one such policy enforcement engine. This is the only open source policy enforcement engine which takes into account Kubernetes structures. What I mean by that is, given the Kubernetes orchestration platform, we have several pods. KubeArmor has visibility and enforcement privileges within this pod such that it can apply policies at individual pod level. With that said, let me go on to the problem statement. Now, why do we really need systems policy enforcement engine in Kubernetes, or for that matter, anywhere, even on the virtual machine or bare metal? The primary point is, we have been dealing with network-related attacks for quite some time, but some of these attacks may not necessarily end up coming from the network. For example, if there is a supply chain attack wherein the Docker images or the container images are already compromised, which means that by the time it gets deployed in the environment, the attacker is already inside your pod. How would you limit access to such an attacker when the attacker is already inside your pod? Or we make an assumption here that given the network primitives, it is quite a possibility that an attacker can enter within the pod and sit there waiting for an opportune moment to attack the system. What KubeArmor does is it makes sure that there are two aspects to KubeArmor. First is the visibility aspects, using which KubeArmor knows what all things a particular pod or container is doing. What things in terms of systems perspective. What are the processes it is spawning? What are the file system accesses it is making? And it has this visibility information, which is exported as alerts and telemetry back to the system. Secondly, KubeArmor does policy enforcement using Linux security modules. Linux security modules are the only way of enforcing runtime systems policies, be it at process level, be it at file system level. There are certain other primitives that are available, but LSMs are the most famous, most prominent, and most useful. The question is, what are we doing differently? One aspect there is that LSMs typically had been made use of at the host level, not at the pod level in Kubernetes. KubeArmor attempts to bring the same primitives, the same level of protection that was applied to the host, bring it to the pod level as well, which means that within a pod, KubeArmor, as a user of KubeArmor, you can specify a policy limiting what a particular pod can do. So, usually this was handled before using an AppArmor or SLNX policies. That there are multiple issues with AppArmor and SLNX policies used natively. They are very hard to get right. They are very hard to code in the first place. The policy constructs for SLNX and AppArmor are very different. Linux allows either AppArmor or SLNX to be used at a given time. Those are not stackable LSMs, which means that you can't use them in parallel, which means that given a deployment, they will either go with AppArmor or SLNX. The second aspect here that is mentioned is the container runtime security is not equal to say network security, and that is one of the primary message that we wanted to send out. KubeArmor, with network security, you can achieve a lot of things, but there are still a lot of things left unprotected if you don't have systems policy enforcement engine in place. The third aspect is, like I mentioned before, of course, there are primitives available at the host level to protect your host, and Linux kernel have these primitives built in right from the very beginning, but these are not tailored for Kubernetes platform. KubeArmor tries to bridge those gaps, and the runtime security for systems and applications. These are the vital elements for achieving any compliance. For example, let me give you a quick overview of what I mean by that. Here is a snapshot of what you can see: a system versus network-based attack. In the topmost part, you see here are the attacks possible with network-based attacks. So this is a Mitre technique. These are the set of Mitre TTPs. And when you enable network-based attacks, you can see these many set of attacks that are possible using network. But when you enable systems attack for Linux, all of a sudden you have all these many attacks that are possible, all these many TTPs that are enabled, which means that most of the controls, most of the attacks are from systems perspective, and these attacks have not got their fair credit or their fair attention till date in the security community, and that's where those are the gaps that KubeArmor is trying to bridge. Now, next, let me pause here and try to put KubeArmor in the context of existing engines out there. One is, of course, the system policy enforcement is not a new topic by itself. There has been several work done in Kubernetes working groups, and maybe that is something that I should be talking about. One is, how is KubeArmor different from whatever exists today? The first part is there exists something called as pod security policies in Kubernetes. Pod security policies is essentially an admission controller. Now, this is a typical question that I get whenever I talk about KubeArmor, that there already exist Kubernetes pod security policies, and how is KubeArmor different from it? The pod security policy is essentially an admission controller, which means that if you are trying to spawn a pod with if spawn a privileged pod and you want to limit limit spawning of such pods, then you can have an admission controller which can be taken care of by the pod security policies. But KubeArmor is not an admission controller. KubeArmor is a runtime security enforcement engine, which means that you can specify declarative YAMLs at runtime, specifying what are all the processes, what are all the file system paths, a process is allowed or not allowed, and that gets enforced at runtime. One of the other, and one more thing I need to note in the context is, there also exists something called as pod security context. Now, pod security context is very different from pod security policies. Pod security policies is an admission controller, but from the pod security context, if I have to say, Kubernetes already allows you to specify a security context wherein you can specify an SLNX profile or AppArmor profile in the context of your in the context of your pod. Now, specifying an SLNX profile or AppArmor profile for a normal user is not very easy, and that is where that is some of the gap that that is one of the important gap that KubeArmor addresses, and that is what it sets upon. One other comparison I would like to make, a few other comparisons rather. A typical question that gets asked is how is KubeArmor different from something like seccomp profile? Today, Docker and container runtimes allow you to specify a seccomp profile, which can filter a set of system calls that your pod has access to. Uh, One of the primary limitation of such seccomp profile is that those are static in nature, which means that you can apply those seccomp profiles only when the pod is starting. You have to specify the seccomp profile before the pod starts up as a Docker initialization statement. Once you do that, though that seccomp profile stays, you cannot change that seccomp profile for the lifetime of that particular Docker. Only if you have to change it again, you'll have to kill the Docker, you have to kill the container and start it again. In essence, seccomp profile is highly limited because of its static nature. And I don't think there is any comparison between KubeArmor, which uses LSMs for policy enforcement, versus seccomp, which Linux kernel supports seccomp for system calls filtering. These are two different mechanisms altogether for policy enforcement. Now, one more. There are few solutions out there available for the Kubernetes world as well, and the primary one being the Falco and Tracy. Falco makes use of eBPF-based backend. It has a very flexible and comprehensive BPF-based observability and traceability, observability and monitoring engine, using which you can specify the exact fields and specify if someone tries to access that particular system call or a system call with a specific set of parameters, you get an alert. However, the primary difference between such engines and KubeArmor is that KubeArmor is an enforcement engine as well. It's not only an auditing engine like Falco and Tracy. It can also block the object accesses at runtime, whereas Falco or Tracy can only audit a particular system call or a kprobe or a trace point, all the kernel primitives at runtime, which means that once you get an audit event, you can act upon it asynchronously, which means that there are certain attacks you can't avoid. For example, if an attacker is trying to delete a file and you already have a policy saying that if someone tries to delete this file, give me an audit event. But by the time you get an audit event, the file is already deleted. In case of KubeArmor, you can specify that these files cannot be deleted, which means that you can enforce a decision, a blocking decision right when a deletion is being attempted. And that's what sets KubeArmor differently. So with that said, Jeff, is there anything else that needs to be highlighted in the context? Or we can.
No, I think you did a really good job of laying out some of the differentiators and the other ones. And I think just to talk about the open source nature of KubeArmor and the contributions, but we can get to that towards the end. But I think we can go from there.
Yeah. So just before going into the demo, I just want to introduce this architecture diagram that you will see even on the KubeArmor's main page, landing page on the GitHub repo. It shows Kubernetes, KubeArmor, and all the LSMs being mentioned here, and there is an eBPF engine. So what happens is KubeArmor essentially leverages existing LSMs. It could be AppArmor, SLNX, or KRSI. KRSI is now known as BPF LSM. We currently don't have BPF LSM integrated. That's a work in progress, but we are very excited about that, about getting that integrated in KubeArmor, and we'll get that done very soon. The important thing here is that LSMs have been leveraged at the pod level, so you would be able to block things within the pod, and if there are any policy violations or policy audit events, that are captured by an eBPF engine, which, apart from capturing the event, attaches the Kubernetes and pod metadata and then sends it out to the logging systems, which means that you get the events in the context of Kubernetes engine. You know exactly what namespace, what pod, uh, you exactly know what the policy violation happened in the context of which namespace, what pod name, what is the pod identity, and things like that. So that gives you a detail. That's what ties the LSM with the Kubernetes. That's what bridges the gap between LSM and Kubernetes. So with that said, let me quickly take you to getting started guide. And when you land up on the KubeArmor page, you might see you will see a getting started guide here. And the first link here is for the deployment guide. I'll just walk you all through this deployment guide. Now, the first thing to do is, you need to have a existing cluster where you can install KubeArmor. Now, there are certain platforms mentioned here. I'm going to make use of EKS, but we also support GKE Container Optimized OS, GKE self-managed Kubernetes, some local Kubernetes engines as well. Today, I'm going to show a demo based on Amazon EKS, and these are the set of steps. The first step is downloading. So KubeArmor provides a tool, an operator tool, where using which you can install or uninstall KubeArmor. Then after you install the KubeArmor, we'll deploy a sample application and a sample policies. I'll show you what those policies look like. Then we'll simulate a policy violation, and then we'll see how to receive the information about those policy violation using KArmor log as well. So KArmor is the tool that we use for install, uninstall, observing, and logging with functionality. So let me dig into the demo. So I have an EKS cluster running. It's just a bare minimum EKS cluster. It doesn't have KubeArmor installed right now. It just has a single node as of now, and it's running Ubuntu 20.04. What I'll do is I'll just follow the set of instructions here. First of all, download and install the KArmor CLI tool. And there we go. We have the KArmor tool installed in /user local bin. So you should be able to check the version. And it says KubeArmor is not running currently. The next step to do would be to install the KubeArmor once you have downloaded the KArmor CLI tool. And let's do KArmor install. So it auto detects the environment, it installs the CRDs, the custom resource definitions for KubeArmor policies, KubeArmor host policies. It creates the service account, cluster role bindings. There is a KubeArmor relay service. Now let's have a look at what are all the different pods that are created. Okay, so looks like the KubeArmor is already installed and running. We have KubeArmor host policy. Using this host policy, you can apply policies at the host level, basically at the worker nodes level. KubeArmor policy manager, basically this takes care of applying policies for the pods. KubeArmor agent is the one which orchestrates the policies, have the watches, Kubernetes watcher events. If any pod goes up or down, or if a new namespace is created, or if a policy is deleted or added, it waits on all these events and takes action in the context. KubeArmor relay service is the one which waits on all the events, the alerts and telemetry events for KubeArmor. And you can connect to this relay service if you want to get a visibility into what's happening in the context of KubeArmor. So yeah, so this is a sample output of KubeArmor install. This is the same thing that you have seen just now. Now we'll install a sample application. This is we call it a multi-Ubuntu application. It's nothing but an Ubuntu image with all the tool sets within it. So I'll just go ahead and install the sample application. And right now, as of now, I'm just following the deployment guide that is present on the GitHub repo. Okay, so it says it is created these deployments. It will take some time before the deployments are up and running. I'll just let's wait for the deployments to start up. Okay, what KubeArmor does is whenever a deployment is deployed, it will add AppArmor or SLNs with annotations depending upon which LSM is used for enforcement on the given platform, and then enable update it does a rolling update of the deployment. So now you see the deployment, the Ubuntu deployment is running. All the 5 deployments are up and running. Now we have a sample policy. Let me show you what the sample policy is. Yeah, so this is a sample KubeArmor policy, and the name is this. It operates on the namespace multi-Ubuntu. It blocks the sleep command. So if someone tries to invoke the sleep command within this namespace, within this pod with the label group1, then it will block the process execution for this particular path. Now, group1 is a label in the context of Ubuntu 1 deployment. Let me do a policy violation now. So what I will try to do is now try to invoke the sleep command. So Ubuntu 1 has the label group-1. So I'll try to log into the deployment or into the pod, and I'll try to invoke sleep. So right now you can see that the sleep is invoked. It sleeps for 1 second and comes out. We want to apply a policy using which this can be denied. So I'll just apply this, deploy the sample policy that I copied before. Now I'm applying the policy. And the policy is created. You should be able to check using kubectl get KSP. It's part of multi-Ubuntu namespace. So in the multi-Ubuntu namespace, we have a policy named as proc path block. And now if I try to do the same execution again, I'm logging into the Ubuntu 1 pod to try to execute sleep1. And there we go. There's a permission denied. So this policy is now applied on this particular pod, and we have sleep execution getting denied. So one of the question is, it's great that the policy is enforcing. How do you get the policy context? How would you get the alerts and telemetry information that is generated in the context of policy? And for that, we have made it easy using our KubeArmor CLI. All you need to do is do a port forwarding. So I forwarded the port for KubeArmor, and I can now use KubeArmor log, KubeArmor CLI, KubeArmor log. So you can see that the KubeArmor log is connected to the port forward to this service. Now, if at the same time, if I try to execute this, we should be able to see the logs. I guess. there seems to be some issue with the login. So ideally, you should see up the logs coming up here in the context of this policy violation, and it should show up here. Well, that's about it. That's the overall demo. Uh, Jeff, is there anything else that we?
Yeah, one question. What were some other basic security policies that people should think about when trying to introduce KubeArmor into their workflows? What are some other contexts that people can help really see the power of what this brings on the security landscape?
Yeah, so let me open up a few sample policies and maybe the detailed specifications, security policy specification. So this specification gives you an idea about what are all the possibilities in the declarative YAML for KubeArmor policy. You can specify severity, tags, message for a given policy, the selector labels, usual thing. Then you can have process. Processes can match a process path. It can match process directory. So for example, you can say that all the processes found within a particular directory will be allowed or blocked. It could also do pattern matching, which means that you can specify a regular pattern for process blocking the process. The same thing is applicable for not only process, but as well as files. You can have match paths, directories, and patterns. So you can say that no one is allowed to access a particular file or a directory or a particular pattern, regular expression pattern. And the owner only flag says whether only the owner is allowed to execute or access that particular file apart from the owner. Now this owner is a Linux user. Every file on a Linux system has a corresponding user. So only that user is allowed and everyone else is blocked. So all these kind of settings you can specify. In the match directories, you have additional setting called as recursive, which means that not only that folder, but all the folders recursively won't be allowed or will only be allowed. Similarly, you can block or allow network protocols. You can say only TCP communication or TCP and UDP communication is allowed. ICMP communication is not allowed. And again, all this you can specify in the context of a given process only, or if you disable this, it is applicable for the full pod. And the last aspect is capabilities. You can specify what capabilities are allowed and what capabilities are disallowed. Linux systems allow you to have several capabilities which are listed here. You can enable, disable any of these capabilities through KubeArmor. So this basically gives you a good control over the pod in general. You not only can you control processes, files, network operations, but you can also control capabilities at a very granular level. Well, capabilities can also be controlled at a different level. For example, it is possible to have control the capabilities using a pod security policy, but pod security policies today are getting deprecated. Additionally, what KubeArmor allows you to do, if you can enable or disable capabilities at runtime. For example, it means that you can specify a policy, or you can have a policy mechanism where for the initial 10 seconds, once the pod is started up, you will allow all the capabilities, but once the startup is finished, you can block the capabilities. So that kind of dynamic control, it is possible to achieve with KubeArmor. And here are some of the sample examples, security policy examples that we have. One is the blocking the sleep command, like we have seen before. This example blocks all the processes within a /sbin directory. again, this is the important differentiation when it comes to KubeArmor can block the process execution or a file system path access, unlike any other auditing engine, which can only audit an action but cannot block it. So this particular page gives you all the details of what are all the policy examples that are possible. This is match directories, but with recursive as true. All the folders and subfolders within /user are not allowed to, none of the processes from those folders or subfolders will be allowed to be spawned. Similarly, you'll find other examples of process as well as files. Here it says that, only allow processes in the bin folder, and allow directories or match directories for /credentials recursively, and allow only those. All these kind of examples are specified here. There are a lot of examples here that one can go through.
Yeah. There's a lot of detail that kind of runs through this, and that's the power of Kubernetes, of course, is the ability to automatically redeploy failed nodes, and this allows the security for what is being introduced here with KubeArmor, is the ability to protect it at the individual pod, at the pod level, or overseeing all the pod levels, and it's very powerful to see that happen, and all of it's done through a simple YAML file, which is easy to read and interpret the policies and adjust, which is very easy to see the simplicity, but also the power that's introduced here. So thanks for walking us through that.
Thank you, Jeff. These are the other examples. And now I know that there are certain possibilities that you can block ICMP packets using a network policy enforcement agent such as Cilium or Calico, but doing it at the systems level gives you a much lower performance over it. For example, the way in which any network policy enforcement will block it, it operates at a packet level. KubeArmor operates at an object level or a system call level, which means that if someone is trying to access a network file object using a protocol ICMP, it will block that itself. So that's it. Is there anything else that I can add on? We talked about KubeArmor. It's different.
Yeah, the thing I would talk about with KubeArmor is just digging more into the repo and a quick show of how people can contribute, find, and download what we're doing as those walkthroughs. I think you touched on the repo already, but
yeah, let me quickly walk through how the repo is organized, and it's nothing different than how most of the other standard Golang based repos are organized. We have KubeArmor, which contains the most of the code. This monitor is the code which does eBPF based monitoring. Then we have common code, core code, which does which handles all the kube updates. So this has all the watcher related code, and most of the event based handling happens in this particular code. Then there is all this is managed through we have templates based on these are the SLNX templates. These are a set of BPF bytecode. This generates a BPF bytecode internally. This C code generates a BPF bytecode. And then there are common, this is a build folder, which allows you to build the Docker image for KubeArmor, KubeArmor SLNX, and several others. So this is what pushes the binary image to the Docker Hub. And then
we'll also talk about some of the environments as well, KubeArmor.
Yeah, so let me introduce some of the environments that KubeArmor supports. KubeArmor supports, we have tested KubeArmor on GKE and EKS primarily today. Primarily EKS has been used on Amazon Linux 2. We have tried Ubuntu. We have tried container optimized OS. All this information is present in the deployment guide. Like I mentioned before, all the Kubernetes platforms that have been tested tested here. Again, this is not an exhaustive list. These are the platforms that we actively make use of. Self-managed Kubernetes is what the default development environment is based upon. Local Kubernetes engines, we require support of certain ISOs in Minikube, which supports AppArmor. So those ISOs are used with Minikube. Same is true for K3s and MicroK8s. Container optimized OS already supports AppArmor. KubeArmor leverages the same thing. And in case of EKS, we support. So in case of EKS, the example specifies about Ubuntu 20.04 and Amazon Linux 2. These are few of the things that we have tested today. AKS testing is something ongoing right now, but we see not much issues with AKS because we see that most of the AKS images already support an LSM, either AppArmor or SLNX, and most of the latest kernels that we see, Linux kernels that we see, are already shipping BPF LSM by default, which is a very good news for KubeArmor.
So we're getting to the end of our time, but one of the things from the community that maintainers of KubeArmor, such as yourself, are really looking forward to get? One of some of the early asks that the community can help as they get involved, further involved in KubeArmor.
Yeah, I mean, we certainly depend upon community for a lot of things. First major important reason why we have open sourced this policy engine is because as a security product, it does not make sense for us to not have transparency at the code level for any security product that we develop. So KubeArmor has been fully open sourced right from day one across all the platforms, including its visibility solution, including its enforcement solution. There is nothing closed source in case of KubeArmor. But the primary in the security community, having a security enforcement engine is one aspect, but building policy templates on top of that security engine is a different problem altogether. There are multiple ways in which we will look at the community involvement. One is you make changes, you support, you add support for KubeArmor for newer platforms. It could be AKS, it could be VMware Tanzu, it could be OpenShift, it could be anything. There are so many platforms out there, and the core maintainers team won't be able to handle all these platforms by themselves. We look at the community engagement there. The second aspect is, like I mentioned, the policy templates itself. With more and more pods KubeArmor getting tested on, we'll see more and more policy templates getting generated for or being developed for predefined workloads. For example, Nginx or top 10 or top 20 or top 50 workloads, we can have policy templates. So that is where we look for the contribution. There's several contributions. No contribution is less. It could be documentation. It could be just trying out the documentation and giving feedback on the Slack channel. All these are things which we highly welcome and really appreciate.
Great. Well, thank you for your time, and thank you everyone for questions and walking through this demo. Like we said, we'll see you on Slack and the repo and GitHub, and we look forward to engagement for the community as we continue our office hours. So thank you much everyone for your time, and have a good rest of your week. Thank you.
Thank you, Jeff.